In the ever-evolving landscape of artificial intelligence, generative adversarial networks, GANs, stand as a testament to the ingenuity of researchers in creating systems capable of generating novel, realistic content. Conceived by Ian Goodfellow and his collaborators in 2014, GANs have since become a transformative force, revolutionizing various domains from image synthesis to art generation. This narrative traverses the historical journey of GANs, exploring their inception, architectural innovations, applications, challenges, and the profound impact they have had on the field of AI. The story of GANs begins with Ian Goodfellow and his collaborators presenting their seminal paper, Generative Adversarial Nets, at the International Conference on Neural Information Processing Systems, NIPS, in 2014. The fundamental idea was elegant in its simplicity: pit two neural networks against each other, a generator and a discriminator, in a competitive game. The generator's role is to create synthetic data that resembles real data. It starts with random noise and refines its output through training, attempting to generate content that is indistinguishable from authentic data. The discriminator, on the other hand, is a binary classifier that evaluates whether the input it receives is real, from the dataset, or fake, generated by the generator. Its objective is to become increasingly proficient at distinguishing real from generated data. The training process involves a constant feedback loop. The generator aims to improve its ability to deceive the discriminator, while the discriminator strives to enhance its discriminative prowess. This adversarial interplay propels both networks to refinement, eventually converging to a state where the generator produces highly realistic content. GANs introduced a novel objective function that involves a minimax game. The generator minimizes the log probability of the discriminator being correct, while the discriminator seeks to maximize this probability. This adversarial training ensures a dynamic equilibrium, pushing both networks to improve continuously. The incorporation of random noise as input to the generator fosters diversity in generated outputs. This stochastic element introduces variability, preventing the model from memorizing specific instances and promoting the creation of diverse content. Over time, researchers extended the GAN framework with innovations like progressive GANs. This approach involves training the generator and discriminator progressively with increasing image resolution, allowing for the generation of high-quality, high-resolution images. GANs made an immediate impact in image synthesis. They demonstrated the ability to generate realistic images, leading to applications in face synthesis, style transfer, and even the creation of entirely fictional images. GANs showcased their creative potential in the realm of art generation. Notably, the introduction of DALL-E by OpenAI demonstrated the capacity of GANs to generate diverse and imaginative images based on textual descriptions. GANs found utility in enhancing image resolution. They were applied to the task of super-resolution, generating high-quality images from low-resolution inputs, with applications in medical imaging and satellite imagery. GANs are susceptible to a phenomenon known as mode collapse, where the generator produces limited variations or even replicates a single mode in the dataset. This challenge has spurred ongoing research into mitigating mode collapse and enhancing the diversity of generated content. Achieving stability in GAN training remains a challenge. The dynamic nature of adversarial training can lead to oscillations and difficulties in convergence, necessitating careful tuning of hyperparameters. The power of GANs to generate highly convincing synthetic content raises ethical considerations. Issues such as deepfake generation, where realistic but fabricated content can be indistinguishable from reality, have sparked discussions about the responsible use of GANs. Researchers extended the GAN framework to conditional settings, giving rise to conditional GANs, (CGANs). These models enable the generation of content based on specific conditions or labels, enhancing control over the generated output. Style GAN and its successor, Style GAN2, introduced innovations in controlling the style and attributes of generated images. These architectures demonstrated remarkable capabilities in generating highly realistic faces with controllable features. GANs have been leveraged for unsupervised representation learning. By learning from unlabeled data, GANs can discover latent representations that capture meaningful structures in the data, contributing to advancements in feature learning. GANs have been applied to medical image synthesis, generating synthetic images to augment limited datasets for training diagnostic models. This has implications for improving the robustness and generalization of medical image analysis algorithms. GANs have become a valuable tool for data augmentation. By generating synthetic data, GANs aid in training machine learning models, particularly in scenarios where acquiring extensive label datasets is challenging. The fashion industry has embraced GANs for designing new clothing styles, generating unique patterns, and even predicting upcoming fashion trends. GANs offer a creative tool for designers and marketers in the fashion domain. As of the present day, GANs continue to be a dynamic area of research with ongoing innovations and applications. Researchers are exploring improved training methodologies, addressing ethical concerns, and extending GANs to novel domains such as video generation and text-to-image synthesis. Generative adversarial networks have emerged as a tour de force in the realm of artificial intelligence, pushing the boundaries of what machines can create. From their inception in 2014, GANs have sparked a creative revolution, transforming how we approach image synthesis, art generation, and various other applications. The journey of GANs showcases not only their remarkable capabilities, but also the challenges and ethical considerations that arise with such powerful technology. As researchers continue to refine and extend the GAN framework, the impact of GANs on the landscape of AI is bound to reverberate across diverse domains, ushering in a new era of computational creativity and generative potential.